This will be the first of a series of examples on using Gauss's law. We've seen Gauss's law, which says this: the electric flux, which is calculable as the closed integral. This is the electric flux through a closed surface, I might add. The integral over the closed surface of E dot dA. And this is just the definition of electric flux. I should really put that there to tell you that it's a definition. De Gauss's law involves this term and tells you that the electric flux through any closed surface is equal to the charge enclosed by that surface divided by the vacuum permittivity epsilon naught. All right, so the first example we're going to do is a charged conducting sphere. So I'm going to have a conducting sphere here. And I know that it's charged to some plus Q. Now, I know some things about conductors. I will remind us all that this is a conducting sphere. I know that on conductors, if I put a charge on it, because the charge is mobile, it migrates to the outside, and so I get a charge that is around the surface. I should say over the surface, because this is really a three-dimensional surface. I can't draw it as such. Maybe someday we'll have 3D drawing pencils. But the idea is this charge deposits itself and distributes itself around the surface, and so that inside there is no charge. So when I write this plus Q, that's not telling you that it's inside. That's just the total charge on the conducting sphere. All right, so what I'm going to ask now is for the electric field inside the sphere and outside the sphere. And in point of fact, we actually already know both of these answers. Because this is a conductor, from previous work, we know that the electric field inside is identically zero. And from the last video we know that the electric field outside is going to act exactly like a point charge, KQ over R squared. So I suppose we should give this thing a radius. Let's give this a radius A. So E1 is valid for E1 is equal to 0. This is valid for any R greater than A. less than A, sorry. Any R less than A. E2 is equal to KQ over R squared. This is valid for any R greater than A. But what I want to do in both of these, both of these results we've arrived at from previous work. What I want to do is do these problems with Gauss's law, just kind of as a way to remind ourselves that, hey, this thing works. So the first thing, let me evaluate inside. I'm going to do this in red. What I'm drawing is an outline of my Gaussian surface. And so I'm going to, remember my Gaussian surface is the tool that I'm using. It's an imaginary surface that I draw, and it's a tool that I'm using to evaluate the electric field at certain points. So I'm going to draw this thing inside, and I'm going to draw it as arbitrarily close to these charges as I want to, and yet not including those charges. To include those charges, if they're truly residing on the surface, I'd have to draw this, this Gaussian surface outside my sphere. But I'm going to draw it inside the sphere, right up to those charges, but not including them. My Gaussian sphere, I should say, has a radius r. I mean, make sure you can see that. Yeah, I think you can see that. Radius r. So what does Gauss's law tell us? Well, it tells us that if I integrate the electric field dot dA, this is inside the sphere, I get Q enclosed over epsilon naught. Now, sometimes when I use Gauss's law, it's easier to look at the left-hand side. In this case, if I don't know what the electric field is, then this doesn't really help me. But I can look at the right-hand side, and my Gaussian surface has not enclosed any charge. So Q enclosed is exactly 0, which means the left-hand side is exactly 0. So the only way for that to happen, because dA, or the integral of dA will not be 0, but the only way for that to happen is for the electric field to be identically 0. We already knew that, but I just wanted to show you that it does actually work here in this situation. Let's do the region outside. So I'll redraw. Here's my conducting sphere, charge Q. This time I'm going to draw my Gaussian surface outside, and again, I can put this wherever I want to as long as I maintain appropriate symmetry, right? This will have some radius r, and what do I get? E dot dA is equal to Q enclosed over epsilon naught. Well, now I need to deal with the left-hand side. From previous work, I've set this up. As long as my Gaussian sphere is concentric on my actual sphere, I get this lovely situation where E and dA are collinear, and this dot product just becomes the scalar answer, which is integral E dA is equal to Q enclosed over epsilon naught. Well, what is Q enclosed? I've enclosed all of the charge, right? I've enclosed plus Q, and that's going to be over epsilon naught. Okay, again, because of the symmetry, this Gaussian sphere is concentric on the sphere, so it's every point equidistant from the center of the sphere, which means E is going to be everywhere uniform, so I can pull that out of the integral. E on the integral of dA is equal to this. Well, the integral of dA is just A is equal to Q over epsilon naught. Area of a sphere, E times 4 pi r squared. Again, I'm using r because this is the area of my Gaussian sphere. So go to Q over epsilon naught, then solve for E. Turns out E is equal to 1 over 4 pi epsilon naught times Q over r squared. I've written it in this sort of strange way because we recognize this as our Coulomb constant K, Q over r squared, which I already knew. But again, I knew that from previous results. Interestingly enough, I knew this because I did Gauss's law on a different problem on the last video. But this turns out to be a general result. As long as you are outside this charged object, all of the charge acts like it's a point charge located at the direct center. Interestingly enough, there's a Gauss's law for gravity as well. As long as you're outside the mass of an object, all the mass acts like it's concentrated at the center as a point mass. And so if you're in orbit around the Earth, it doesn't really matter to you that the Earth is an extended object. You act as if it's a point mass, and you're orbiting this sort of cluster of gravity right at the middle. So there's a Gauss's law for gravity. This is Gauss's law for electricity, and there will be more examples to follow, but this is the simplest one we can come up with. Next, we're going to do an insulating sphere, and then we're going to do an infinite line charge, and then we're going to do a more complicated situation where I have an insulating sphere surrounded by a conducting spherical shell. So you can get pretty interesting with Gauss's law problems. As long as you have the appropriate symmetry, they are pretty easy to handle.